Thank you all for coming for another lecture of the Phyllis and George Harborne Radio Astronomy series. We are extremely grateful to the Harborne family for their continued support of this series for the last several years. The chair of our department has also provided videotaping of this series, and in fact all lectures that we've recorded are online, and you can actually see them right here. So I hope you get a chance to look at some of the past lectures that we've had. In previous 20 plus lectures that we've had, we've mainly focused on radio observations and experimental work. Today we're going to focus mainly on understanding of some of these radio data that people have taken over the years. And in fact, we're going to focus more on jets, the history of jets, and perhaps no one is really more suited to cover this topic than Roger Blandford, who's visiting us today from Stanford University. Roger has broad research interests. These include black hole astrophysics, cosmology, gravitational lensing, cosmic ray physics, and compact stars. He has written some classic papers on the acceleration of cosmic rays in accretion disks, in jets, and also cosmic rays in the galaxy as a whole. Roger took his BA, MA, and PhD from Cambridge University, following postdoctoral research at Cambridge, Princeton, Berkeley. He took up a faculty position at Caltech, 1976, where he was appointed as the Richard Chase Tolman Professor of Theoretical Astrophysics in 1989. In 2003, he moved to Stanford to become the first director of the Kavli Institute for Particle Astrophysics and Cosmology, and the Luke Blossom Chair in the School of Humanities and Science. So essentially, he stopped on every good places in the country, best places in astrophysics. So he's a fellow of the Royal Society, the American Academy of Arts and Sciences, the American Physical Society, and a member of the National Academy of Sciences. In 2008, between 2008 and 2010, he chaired a 2-year National Academy of Sciences Decadal Survey of Astronomy and Astrophysics. Recently, he has received the 2016 Crawford Prize for Astronomy, as well as the Jansky Award for Lectureship in 2019. So with this short introduction, I want to thank him, and let's have a round of applause for Roger. So last thing, please stay around. We'll have pizza at the end.
Well, thank you. Let me begin by relaying my thanks to the Harborne family for their generosity in endowing this lecture series, and I'm very pleased to be here. I'm enjoying my visit much more than my last visit, which was on a review committee of the physics department, and it's kind of you to invite me back. I should also give my thanks to Farhad Yousafzadeh and all the others here for their kind invitation and their hospitality. So I'm having a very good time, and I've already learned a lot from my conversations with here. So thank you very much indeed. I greatly enjoy being back in Northwestern. So what I'm going to talk about, I gave this title of the evolution of extragalactic radio sources, and here my sense of evolution is going to be the development of our understanding of these sources rather than the physical evolution over cosmological time, which is the way most radio astronomers would think about this title. So I'm going to say almost nothing about that, but I will talk about a sort of intellectual history, if you like, of the subject. And I know you've had some historical, or at least I've just learned that you've had some historical lectures, so I shall go rather quickly through this, but as the audience turns over, I think the history is actually quite interesting and instructive, and anybody who adheres to the physics-oriented idea that scientific research consists of refining the details and parameters of a well-defined physical theory by the next experiment, going forward one step at a time and just doing this, should pay attention, because the story I have to tell you is logically unscripted and really quite chaotic, and there's still a lot to be done. This is very much an active field where discoveries are out there to be made. Of that I am more confident than anything. Okay, so let's begin. Oh, that shouldn't have been there. Okay, let me begin with radio astronomy. As most of you, everybody knows, this is Carl Jansky, who was the first person to realize that there were radio waves from out there, and he found the sun and the galaxy. And here he is, and this is his reconstruction at NRAO of the telescope that he used in the 1930s, and this is the Jansky VLA, which memorializes his contribution. The second person I'd like to acknowledge in the history is Grote-Reber, and he knew of Jansky's work and built a radio telescope in his backyard. It's in Wheaton, just down the road from here. So you're at the cradle of radio astronomy here, and it's remarkable. And he was a remarkable man. I had the pleasure of meeting in I guess it was the 1990s, and there was a big argument between him and the optical astronomers about the history of astronomy. And I remember listening to this, and we looked it up afterwards. He was right. So he was iconoclast, and he did everything himself his own way. And boy, it was started a field. And one of the radio sources that passes overhead here, and of course just down the road, is Cygnus A. And so here is this is essentially Jansky's map of the sky. He was the first person to see sort of sources out there rather than the galaxy itself and the sun. And there's a long sort of intellectual history that's encapsulated in this montage here of early images and early work. And here's J.S. Hay, who actually also met as a student, and Graham Smith at that time. And they, in these early days following the Second World War, where a lot of these techniques had been developed for radar, and so it was used for radio astronomy, they were able to refine the position. And here's Walter Bader and Rudolf Minkowski, and they were able to use optical astronomy to eventually refine this one particular source of radio waves, which had been thought of as basically being a star, and they saw it as a galaxy, and they interpreted it, as did also Hyman Spitzer, who worked with Bader on this, as two galaxies in collision. So originally this was thought to be a star, and it's a natural thing to assume, and then it was found to be something out there, outside the galaxy. In the 1950s, people understood that, and so it was definitely an extragalactic source, but their interpretation was that it was two galaxies that were just crashing into each other. And morphologically, you could believe this, but it became a much more complicated story down the road, and in particular, in about the same time as this identification was made in 1953 or 4, Jennison and Das Gupta were the first people to do very crude form of radio interferometry, which meant you could actually not only get the position of the source, you could also resolve its structure. And what they found was, this is actually from their paper, they found that with a double radio source, what they found is two sources of emission on either side of the galaxy. And that was what they were able to do with the early radio astronomy, and this sort of got better and better as time went on, as people built more and more sophisticated radio telescopes. And then this is a Kirker 1970 map, which showed a now classic structure of these extragalactic double radio sources. And there were two lobes, as we call them. I'll try and use as little astronomical jargon as I can, because but these are sometimes called lobes of radio emission, one on one side, one on the other side. The galaxy is in the middle. And then, as you can see here, there is also a source, essentially what at that time was a point source of radio emission, identified with that galaxy. And these are the early works, and then obviously the theorists got in on the act, and although the idea had been around since the 1940s, it was suggested particularly by Shklovsky, who's here, and also Ginzburg, and actually several other people, Alfvén and others, realized this, that the emission process was not a thermal process, would otherwise, you'd never have seen any of this stuff if you were dealing at the sort of temperatures that would radiate radio waves. It was a highly non-thermal process, and they figured out that it was almost certainly relativistic electrons spiraling in a magnetic field with relativistic speeds and radiating synchrotron radiation, the sort one sees at a light source nowadays, but in the radio band. And then, through a series of arguments, this is Jeff Burbidge, who was probably the first person to sort of get this essentially right. It was realized that this was not a casual matter. The energies that had to be invoked to explain these synchrotron radio sources were colossal. In the case of the source like Cygnus A, you were looking at perhaps 10 to the 5th to 10 to the 6th, nearly a million solar mass c², rest mass of a million solar masses up to. Actually, the other sources are more energetic, but it was realized that these were colossally energetic phenomena, even by the standards of a galaxy full of stars. Sort of parenthetically, this time, it was still thought originally that these were two galaxies essentially in collision. And there's some poetry that I remember by a poet called D.M. Thomas, not Dylan, but another one with the almost same name. And he wrote a whole poem about Cygnus A, which I won't recite to you, but I will recite two lines from it, which it's obviously a metaphor with lots of human interest, but he says, but that was in another galaxy, and besides the star is dead. And so that's a good sort of sequence, if you like, to what follows. And so, yes, there's a star there, but it's a dead star, and of course, we should pay more attention to poets when we're struggling with trying to do physics. So I hope you've got that message at least. Okay, so they're extremely energetic sources, and the primary emission mechanism is synchrotron radiation. So here's sort of a slightly modern view of Cygnus A. This is a VLA map, and one of the things that one can see here is something that was actually inferred mainly by Martin Rees, essentially in the 1960s, was that instead of this being the result of one cataclysm, one big explosion, if you like, or one collision, in fact what was going on was that energy was being continuously supplied from the nucleus of the galaxy out to power continuously these two lobes of radio emission. So these two lobes on either side of the galaxy like that were powered by some transfer of energy from the nucleus out to these lobes. And it was a continuous process. And there's an irony here in that Jeff Burbidge, like his colleague Fred Hoyle, in cosmology took the view that the universe was a continuous evolving structure, and they didn't hold with the Big Bang, which was Hoyle's term for was pejorative term for an evolutionary cosmology. They didn't believe in that, but they believed it was continuous. And yet, here, in the case of the extragalactic radio sources, they saw it as one very big bang, as it were. But the story turns out to be that there's a continuous, ongoing process. So there's kind of an irony there. So let me just interpret this a little bit more. So here you can see, in fact, on both sides, if you look carefully, the jets delineated by radio imaging from the nucleus of the galaxy, inflating these two lobes. Here we see it on a much smaller scale, using, this is milliarc second resolution, so this is early, this is not so early, actually, this is not the best, but it's recent VLBI imaging, where you use telescopes on either side of the Earth, basically, to improve the angular resolution. So you look down to angles of 10 to the minus 8 in radians. Okay, so here you see it at on the small scale, and so the power source is then being located to the not just to the galaxy but the nucleus of the galaxy using this image. So you can see this jet here, and these are very common. These are called jets. These features that transport the power from the nucleus out to inflate these radio lobes and power them. Here we see an image made that's a combination of the radio shown here in pink and the X-rays shown here in blue. And so what we have is the hot gas around here associated with, in fact, in this case, a cluster of galaxies. And so there's a lot of hot gas there, and that is obviously a large part of the story, the narrative, that describes the powering of these radio sources by whatever the machine is at the nucleus of this galaxy. And so the conclusion was that powerful radio sources are indeed powered by jets. So just let me parenthetically, for the physicists here, and also because Farad and I were having this conversation this morning and in violent agreement in this business, which is that radio astronomers don't get enough credit. So let me bag on the optical astronomers and say they've just got one measly octave of these 10-gram pianos to deal with, but radio astronomers have these almost 3-gram pianos worth of spectrum to deal with. But they shouldn't get too big because gamma ray astronomers have 4, and so we shouldn't measure everything. And I will say, in defense of the optical astronomers, there's an awful lot of physics going on in the optical part of the spectrum, and a real optical astronomer goes into the ultraviolet and the infrared and so on seamlessly nowadays, and so on. So, but what the more serious point here is, and this is obviously a popular slide, but I think it's very important for physicists to appreciate this, that this sort of, if we throw in gravitational radiation, cosmic rays, and neutrinos, and one day maybe we'll be doing dark matter astronomy, I don't know, but maybe we throw in these non-electromagnetic bands as well. We have 140 octaves, not just one, but 140 octaves worth of thing to do. And even second-rate scientists can make first-rate discoveries given this huge, opening up of the spectra. You're just looking and seeing, and not surprisingly, you get a very different view of the universe and its contents. So that's a sort of trite thing to say, but I think, if you want to think of it in terms of physics, sometimes you go from one atto-electron volt to one zeta-electron volt, the highest energy cosmic rays. All right, the highest energy cosmic rays are all probably at source are pretty close to a zeta-electron volt. And so there's 140 octaves worth of spectrum here to explore. So, and the story of AGN and extragalactic radio sources is one of using all of this. Nowadays, it's actually an old phrase, but from 2 decadal surveys ago, multi-messenger astronomy, which is combining all of this lot, but also multi-wavelength as well. So one uses all telescopes to get the holistic picture of all sources. So, I mean, that's just the natural approach nowadays. And so, whereas the techniques are very specific to the different parts of the spectrum, the putting together the picture requires all of the information. Okay, so that's the right thing. So here's another source. It's called Perseus A. This was I like to show this one because it's actually the first active galactic nucleus. It was discovered in 1908 by Edward Pfaff. He was a graduate student at the time. As you can tell, this is an older picture. And he actually did other things in optical instrumentation that were quite pioneering. But he found this source, which is the radio astronomers will call Perseus A, and the optical astronomers will call NGC 1275. And this source was the first example that was found of the nucleus of a galaxy showing emission lines. And so clearly something was going on there. And it was a great discovery. If we look at it now, it's in a cluster of galaxies. This thing looks like a Halloween mask, eyes and so the rest is actually an X-ray map. And you can see these bubbles here these are the radio lobes that are inflated in this giant puddle of hot gas, and they're even hotter, and they float up like balloons. So they float up subsonically in this, and you can see past examples of radio lobes being inflated now and then bubbling up into the, floating up. And this is the way that, I won't go into this here, that it's believed that these clusters of galaxies are kept hot because they ought to cool, and they're kept hot just like the sun is kept hot by nuclear reactions in its center. Okay, and so if we look at it now with radio imaging, this is actually from radio astronomy from space, and we can now look at these jets, and there's one important feature here that will come out. This is on the scale, this is on a relatively small scale. One sees a very common pattern that the jets, in fact, the emission appears to be coming from the surfaces of these jets. It's as if we've got a boundary, we've got some hydrodynamic flow, for example, and there's a boundary layer there, and it's the boundary layer where the dissipation is happening, and the dissipation corresponds to radio emission mainly by the synchrotron process. Of course, there's much more going on in these jets than just radio waves, but as I like to say, radio astronomy always gets there first and always sees the detail because it's a very much more sensitive technique, and I attribute this personally to the natural sensitivity of radio astronomers. They are personally very sensitive people. If you take a gamma ray astronomer and you hit them about the frontal lobes with a 2x4, they don't notice, but a radio astronomer, the smallest rumor or the smallest suggestion of something out there, and they're rushing around and sending off papers to Nature and so on. So radio astronomy is really a terribly sensitive business and prosecuted, as I say, by highly sensitive people. Okay, so now this one here, I'm going to jump to what is coming up next, is to the chase, which is really these are powered by black holes. And I'll start talking about black holes in a moment. I want to do a little bit more observation, but just to give you a scale, because you kind of know this, just to give you a scale, this is, we're already resolving with these radio observations from space something close to the size of a black hole. And again, you see this sort of edge-brightened structure, and I'll come back to that a little bit later. Okay, so here's another radio source. It's called Virgo A, or those of you who read the above the fold in the New York Times may know it as M87. And here is the person who first found it, Heber Curtis, in 1917 at the Lick Observatory. He actually found the first jet, obviously at optical wavelengths, and he found what he called a curious straight ray coming out of the center of this nearby elliptical galaxy called M87 or Virgo A. It's got other names, but never mind. And here he is here at the Crossley refractor, which he used to do this. And it was a remarkable discovery, and you can sort of see it here in a modern image like that. You can see it. Here's the cluster of galaxies that it lies in. Here's the two jets from either side. You can see this at X-ray wavelengths. You can see it here at more X-ray images. Here's at radio images. So again, we're using the whole electromagnetic spectrum. And one sees again this edge brightening on the outflow. And here we see it more clearly. And there are the jet, and there's jets on both sides. But this is again a feature that one will see for these sources. This is one that is making a fairly small angle, probably about 15 or 20 degrees to the line of sight. So the jet there's two jets sort of like that, and if the camera over there is the observer, then it's sort of like that. Okay, and we'll come back to that point. So now, as you know, if you read the newspapers or beyond that, then this is associated with about a 6 billion solar mass black hole. And as we're asking for millions of solar masses of MC squared to power these sources, then billions is up there. It's okay. It's good enough. Okay, so that's what we have. Now here's another one in the history, and again I'm bringing out some part of the story here. This is 3C273. What you just saw actually was 3C274, but that's kind of, actually it's an interesting story about that, which I will not go into, but this is 3C273, and it's the third Cambridge catalogue of radio sources. It's number 273 in it, and many of the numbers actually vanished. And it was the first quasar. And most people here, I think, know what a quasar is, I hope, as well as a type of TV. It's an astronomical source where typically the optical emission, for the optical chauvinists, sort of more or less outshines the host galaxy. So there's precise definitions, and they sort of don't make a lot of sense. But you know, when you see one, and we know there's a host galaxy here because we can block out this point source of light in the middle, and this one was figured out that it was an extragalactic source because they were stars originally. Again, they were stars for many people. This was in 1963, and my Oswald colleague Martin Schmidt is credited with having taken the spectrum and having understood this was a cosmologically distant source and therefore prodigiously energetic. And before long, it was associated with the nuclei of galaxies. It was found to be rapidly variable. But again, in this sort of radio orientation, this is another former colleague of mine, Cyril Hazard, and this whole business was enabled by his very clever use of the moon to get the position, just like happened with Cygnus A, to get the position of this source so Martin Schmidt would know where to look. And basically, as the moon occulted this source, you were able to get interference, you were able to get diffraction, firstly going across like that, and then the other side coming across like that. And so you get two coordinates, and so you can say X marks the spot, and then you can know where to look. And that was the lunatic fringe, if you like, but it was a very clever technique, and even more impressively, the way it was enabled. And I think he deserves a lot of credit, too, for having made this glorious discovery of quasars in 1963. And so just a little bit more about this. One of the things you see the sources is not just continuum optical emission. You see lots and lots of emission lines showing very high excitation. It means there's a lot of ultraviolet radiation there, and a small amount of gas can reprocess that into typical emission lines you learn about. Those who still learn atomic physics would learn about if they learned atomic physics anymore. So they're all there, and you can use these lines, of course, to get the recession velocity, if you like, the redshift of this, and therefore get its cosmological distance. And so that's the way we know its distance. This, of course, has a jet too, seen radio, optical, and X-ray. Another feature that was actually discovered earlier in other sources, but was actually made most clear by observations by Reed-Head et al. In the early mid-1970s, was that the features in the jet appeared to be moving across the sky faster than the speed of light, a phenomenon known as superluminal expansion. So what one can see here, that's 30 light years. Here's the nucleus, the core, if you like, of this jet, and see this feature here. It's moving from there to there to there. So you can see it move across the sky away from the core faster than the speed of light. So were astronomers renouncing special, not just general relativity, but special general relativity? No, 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 as is taught in freshman physics nowadays. This was actually an effect that was predicted and expected, is if we look even closer to the line of sight. So imagine something coming towards the camera over there as an observer. It's moving almost at the speed of light. It's just an elementary exercise in trigonometry to show that what you will appear to see is moves faster than the speed of light. In this case, it's about 10 times the speed of light across the sky. And that's all that's telling you, is that the jet is making a small angle to the line of sight. And you might say, should I be paranoid about this? All these jets pointing at me, I don't really like this. And the answer is no, 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 because the ones that come towards you, because of aberration effects and so on, are very, very bright. And so you preferentially see the ones that are coming towards you. So any sample is going to see these ones coming directly towards you like that. And so this is an example of superluminal expansion. So many of these jets that are seen in the nuclei of galaxies are selected to be the ones coming towards you, and you have to allow for that effect. Also to remind you that the gamma rays are there, and this source, like many others, is seen as a much more powerful gamma ray source, because remember I said they're much more less sensitive people, the gamma ray astronomers, so you need a lot of power for them to get interested. And of course they're much more powerful in the gamma rays than the radio, and as is true at other wavelengths, but particularly importantly at gamma ray wavelengths, or energies I should say, they're highly variable. Okay? So that again is telling you that whatever's responsible is very compact. That's a sort of temporal argument as well as an imaging argument. So jets can be relativistic, variable, gamma ray sources, and we see them, of course, throughout the electromagnetic spectrum. Okay, so there's now lots and lots of jets that are out there, thousands and thousands of them. Here's just a sort of montage. Some you've seen, some you haven't seen. You can see them here. Here's one in most of these are radio images. This one is actually an X-ray image. It's called picture-ray. You see this source. There's the nucleus of the galaxy, I should say at this point, going across the sky there. There's the beam dump, if you like, at the end of that. And this is, the lobe of emission and so on. But see this dead straight thing. And so we have this jet, which is subject to all the instabilities known to classical physicists, and yet it's able to make a dead straight structure. So they're pretty good engineers out there in the universe. And you see all these other things that have obviously stories associated with them, and everyone has a mother who loves it. And this one's probably a binary here, and so we learn a lot from the whole montage, and a huge amount of work has gone into mapping these things and indeed monitoring them as they change. And so we've learned an awful lot about the physical conditions in these sources. Okay, and the jet phenomenon is not just confined to these extragalactic quasar-like things. Here is just, we see it all over the universe. Here is a Meerkat image. Meerkat is a highly successful South African telescope that's sort of like at the moment is a bit like a VLA. I mentioned that's the one in Socorro, the NRA, but in the south. And it's been spectacularly successful. And here's one. I'll show you something else he did lately. But here's one of the things they did was they just did a little tiny patch of the sky and counted sources there. And you then multiply up to get the whole sky. Then over the whole sky, there's about 2 billion sources they're counting, and 1 billion of these, give or take a few, is basically one of these jets, one of these active galactic nuclei with the jets. The other half are probably things like supernova remnants and so on. And if we had something like our galactic center, which we know is a radio source, I'll come back to that in a moment, and it was on the other side of the universe, as most of these sources are, we'd be at 3 or 4 orders of magnitude too faint to see. So there's a huge number of these sources out there. Here's the Crab Nebula, a supernova remnant. See the jets? There's a spinning pulsar there. Here's a protostar, HL Tau, one of the famous. You may have seen this above the fold in the New York Times. So this has a jet associated with it. Here's SS433, the coming and going source. It's a black hole in our stellar mass black hole in our galaxy that makes precessing jets that sort of I'll do one of them, sort of like they precess on the sky every 164 days, like that. And so you can see the emission lines associated with that precession jet, and the radio emission, the X-ray emission, and so on.
So the movie you showed for SS433 that's a simulation, right?
No, it's real. Those are observations.
This is a composite of observations.
Yes, this is a time series from the observations. This line here is the model, the white line. These are observations.
I remember this above the pole.
We may not have seen that one, but it's real. I'll show you where it came from if you want. Yeah, but I mean this is seen. Yeah. So and this is the multi-messenger part is the neutrinos, and there's been a claim that's sort of on the fence at the moment, I would say, that IceCube, this neutrino facility at the South Pole, has found coincident neutrinos, maybe more than one, from one of these so-called blazars, one of these sources, like a jet coming towards you. And the thing I will say with some confidence is that they're on the threshold of neutrino astronomy of active galactic nuclei. The durability of this particular identification remains to be seen, but it's clear that the capability is there to find out if these are neutrinos. These are PeV neutrinos. These are not MEV neutrinos. These are PeV, million times more energetic. Okay, so this is, and we'll come back to that point again. Here's the 170817, which Vicky knows all about. It was the colliding neutron star, and originally everybody was in on the act. All of these buccaneering astronomers were out there observing it, and then the radio astronomers were kind of bereft because nothing. So sensitive, and there was sort of nothing there. But they're kind of persistent, and everyone said, give up, But nope, one of them in particular did not. And of course, in the course of time, they found the jet. There's jets. So there are all these theoretical papers appearing saying, here is why there are no jets in this source, and so on. But patience, you find the jet. So here's the jet.
A couple of them are in the room.
Yes, absolutely. Yes, I clearly I've gone too far. So I apologize for whatever I've just said. Okay. Or congratulate you for whatever I've just said. One or the other. Okay, all right, here we go. So let me now segue into the heart of the matter, the vasty deep, the black holes. And so let me go quickly through history and so on. A German soldier who happened to also be a temporarily displaced observatory director called Karl Schwarzschild used the new theory of general relativity to solve for a spherically symmetric solution, and which is a Schwarzschild solution, which most physicists now know about. And he didn't recognize it as a black hole, but we now do. In 1963, Roy Kerr found at that time a miraculous solution to these equations that describes a spinning black hole, and was invoked almost immediately. It's the same year that quasars were discovered, and that connection was made pretty fast. Zeldovich, Wheeler, Sharma, all of these people, a lot longer list than I've got time to fit on here, were people who at that time sort of did make the connection with black holes, but rather tentatively. But in practice, what happened was the microwave was discovered in that way, and they thought cosmology was even more interesting, and so most of them got distracted into astronomy, and so a range of other possibilities were were also considered. In 1971, black holes were sort of demonstrated, and I'll say a little bit more about this. Cygnus X1, M87, the observations of that took place. Sag star that's just astro code for the nucleus of our galaxy. Disks and jets were understood. The binary pulsar was seen, which two neutron stars which had to make a black hole in its future. Black hole binary mergers, as you know, in 2015, the neutron star binary mergers, the Event Horizon Telescope in 2019, and so on. So that's the observational story. So the black holes themselves are sort of anticipated by John Mitchell and Karl Schwarzschild here. And obviously, I'm not going to go through this. You know that there's an event horizon from which light cannot escape, classically, and that's a structure which really is structure. And so there was the idea that black holes could exist. Historically, white dwarfs were understood by Chandrasekhar and neutron stars by Oppenheimer in some simple way, and general relativity was part of this, but the astronomical part of this story was that we had maximum masses to the white dwarf stars and the neutron stars, and if you got more mass concentrated, the center cannot hold, and you would have the black hole form there. That would seem to be inevitable, which was a conclusion that was resisted on not terribly good grounds, but it's one that we now strongly believe. Here were the observations from the 1970s, and what we see is a binary star. Here, this is a cartoon, obviously, of Cygnus X1, a bright blue star aside it, an accretion disk there, and there in the middle, a black hole. And this accretion disk is what you're looking at, and doing the dynamics. And so, historically, this was, for most people, the proof that black holes really did exist. And so here, you've seen this one before, I'm sure. Let me just move on. It's tremendously important, black holes, seeing so the actual sort of theory is consistent with the observations of the gravitational radiation waveform. And that's important for heretics who believe that there are funny fields or poking out of these black holes or funny surfaces there. The sort of classical theory, if you like, of black holes, as I said, Roy Kerr I've mentioned, here's Roger Penrose, who had some very important physical eyes, John Wheeler, who led a team of people who did this and had strong insights himself into this, and he's actually credited with coining the phrase black hole, although in fact he didn't. I think he was not the first to use it. It was an Australian journalist called Anne Ewing who used it 2 years earlier, but I think it was original for him. And then here's Stephen Hawking, who particularly in the quantum, actually both in the classical and in the quantum parts, made major contributions to our understanding of the implications of the Kerr metric. And so there's the Kerr metric, which and here is an important point that really came out of essentially a realization from Roger Penrose, and it wasn't put in this form by him but by others. But is that if we consider the total mass of a black hole, there's energy obviously associated with it, and that mass, if it is spinning, as the Kerr black hole describes, if it's spinning, that mass has a part that is extractable and associated with the spin. And if you do sort of thought, in his mind, if you did thought experiments, you could actually take that mass out. So you can get mass out of a black hole by doing thought experiments, and it's the rotational energy, and it can be as much as 30% of the rest mass energy can be rotational. Okay, so that's a very important point for what I have to say. And so the bottom line of this is that black holes are extraordinarily simple. And although they can be generalized in many ways using the febrile imaginations of theoretical physicists, and they're useful in a very formal sense, the ones that poor stumbling astronomers actually encounter are characterized by just two numbers, their mass and their spin. People often talk about charge, but there's no good, the ones that they see should be uncharged because they discharge immediately. So essentially plasma processes will get rid of any charge that they may have. So the ones that actually exist out there that we have any reason to believe are just characterized by mass and spin, just two numbers. That's all it is. And we can measure this. Let's look at our Milky Way galaxy. This is just but one example. Andrea Ghez, I see, came here as a Harvard lecture, so he must have told you a lot about this. Those of you who were present at that, this is what the center of our galaxy looks like. That's what it looks like in X-rays. Here's the trace. This is not a simulation. This is the tracing of the stars. This is done by the Keck telescope, but it's also done using a European telescope. And you can see them in orbit. And just like you do for the solar system, you can figure out there's 4 million solar masses there. Here's some research that Lena Merchikova did. I was talking with Fahad this morning about, and basically this is an observation. I show this because it's radio astronomy again, looking at gas that may be swirling around this black hole, and there are other interpretations, and it looks like you're seeing some red-shifted gas and some blue-shifted gas, just as you would expect from a disk, but there are other interpretations. So this is from the work of Lena Merchikova. Here's the Meerkat again. I promise you this again. This is an image they made. It's not the best representation of it, but you can see a large region around the galaxy, and you see these filamentary structures that most of us believe are magnetic fields. Some believe they're cosmic strings, but never mind. So we think they're magnetic fields, and we can talk about that. And so again, radio astronomy in action. Radio astronomy telling us about the environments of these black holes. Here's infrared astronomy in Chile, using the European telescope, Reinhard Genzel and others, and they are seeing magnetized clouds in orbit around our black hole every 45 minutes. So again, there's a lot we're learning about these objects, and it's ongoing. It isn't the end of the story, it's the beginning. If we want to know about the masses of the black hole, I said there were two parameters, the mass and the spin. So the mass we can get essentially from using Kepler's laws for stars and gas and so on, and it looks like it's correlated with the type of galaxy, with essentially the size of the galaxy there. And so we've got a lot of these masses, and they go up to the champion in the Guinness Book of World Records is 20 billion solar masses. We're down here at 4 million. So, but don't be ashamed. We wouldn't want to live next to a quasar. Trust me. Now the point about the mass is that it gives you access to gravity power. This guy here, Sisyphus, you probably, some of you may relate to him. He rolls a 10-ton boulder up a 100-meter hill and watches it roll downhill and release energy. So it's 3 kilograms of TNT, 300 grams of gasoline, alcohol, or candy. Think about that. 100 micrograms of uranium, you know what that means, and 300 nanograms of accreting onto a black hole. That's the equivalent mass. So gravity power is very efficient. Okay, more than nuclear. So first catch a black hole and all our problems will be over. Okay, all right. And then the spin, we can use the X-ray astronomer. There are other techniques to use to measure the spins of these black holes. And the bottom line is, in the ones that we can measure, many of them are spinning nearly as fast as they can. I won't go beyond that. And they can be spun up faster, of course, by accreting gas or stars or any other rubbish you want to throw at them. Okay, now here's the point. I said gravity power will access the incipient energy of the black hole. Rotational power is also there for the rotational energy is there for the taking, and the way we suspect this happens is sort of just using the elementary ideas back to Michael Faraday and so on. Got a spinning black hole, stick some of this ubiquitous magnetic field through it, and make a Faraday disk, essentially. And there's the light bulb, which is synchrotron radiation for the gratification of radio astronomers. And so you can get that energy up. So if you just use simple electromagnetic arguments in a relativistic context and use Ohm's law, then this will make a zettavolt in a quasar. That's the characteristic speed that you'll make. The current will be 10 examps. And if you're working with the particle physicists, you've got a fraction of a few milliamps is what you're using in your beams. This is 10 examps. For those who don't know XSI units, that's 10 to the 19 amps. This is 10 to the 21 volts. And this is adequate to accelerate the highest energy cosmic rays. Okay, so that's one of the important things about this. It can make the highest energy cosmic rays. The characteristic power is essentially the product of those two numbers, and that's the power of a powerful quasar. Okay, it's just as simple as that. And so the way you extract this energy is to stick magnetic field lines across the event horizon, make a unipolar inductor or do electromagnetic induction, drive a current around the circuit, and extract it with a light bulb at the end. Okay, and there's simulation showing this sort of thing going on. You can see it wobbling around and so on. And this is a simulation that has gas around here that's confining the magnetic field. And that would be important for what I have to say in a moment. So if we use this in M87, it's in the distance of about 70 megaparsecs. That means 50 million light years away. It's a giant galaxy in a rich cluster. This is the image that everyone's seen. There's a 6 billion solar mass black hole there, and that means it's 4 microarcseconds is that the angle it subtends. And there are prominent jets which we know about and you can model and so on. When I first got access to this image, I was excited to see it, and I sent it to one of my colleagues, and she said it's all a cover-up. This is what they've actually got. And they've only shown you this bit. This is actually what they're looking at. Never mind. Anyway, so this is M87 again. Don't trust the government. Okay. So here's this on different scales, this sort of Matrushka doll, sorry, coming down to there's the sort of image like that. And I'm going to harbour on this a little bit, and we can see on these different scales the structure in the jets down there. So this sort of just summarizes more or less what I've already said. Okay, so there are many simulations of this, and I'm now going to go off the reservation. I think that's probably not the right thing to say, but I'm going to go into territory which is regarded as, at best, heretical, and in many other spheres perhaps not, perhaps even somewhat crazy or misguided, but I'm going to take you down an alternative view of what these observations are telling you. So this is a little bit for the sort of more professional astronomers here, but I think I may try to make it accessible to the physicists as well. So basically the standard way, and I've been part of this story for nearly 40 years, of thinking about these jets, is that there really is a spinning black hole. You really are extracting the power for the jet from this, but what collimates it, what makes it jetty, is a whole lot of gas around it, and it's a thick orbiting disk that's orbiting this, that's holding everything in place. Okay, and these are some simulations shown by Ronatal, but Sasha Tchaikovsky and his colleagues who are here do many other simulations, and I've actually been a collaborator on one or two of them with him, and it's a viable and still a reasonable idea of what's going on. But I want to present an alternative view. So this gas has density, it has pressure, it has velocity, it has magnetic field. It's a fluid. It's a relativistic fluid, but it's general relativistic. There's radiation in there too, propagating magneto-hydrodynamics. That's what it is, and that's what these simulations are doing. And so this may yet turn out to be right, but I think the power of the jets is much greater than the power one sees in these objects, and I'm worried by that because I think these things ought to be much brighter than they're seen to be. And I think there are other problems with it anyway. So at least that motivated me to think about an alternative view, which is shown here. And this is the alternative view, is that we have a spinning black hole here. There's magnetic field, these green lines here. Magnetic fields are always green, so we have, well, around here they are, except when they're white. But here we've got the field lines here. And normally what happens if you've got a spinning black hole, you'll make these, if you make a sort of simple structure, you'll make this magnetic structure like this that takes energy and angular momentum away from the black hole and forms these jets. And the alternative view is that there isn't a giant ring of gas here, a torus of gas here that's collimating all of this, but there's more magnetic field. The whole thing is essentially a magnetically dominated structure with the only purpose of the plasma is to defy currents and charges, not any inertia or pressure or anything. And that's obviously an extreme case. Now, if you make a model like this, the first thing you discover is that the energy and angular momentum, if it's stationary and axis symmetric, goes along the field lines like that. So there's no way that you can power field lines here because it's just going to sit there. There's no source of energy and momentum. But the innovation is that, in fact, this structure with these magnetic field lines moving past each other is highly unstable, just like accretion disks are unstable. And energy and angular momentum is efficiently transported not just out along the jets, but also, not just up, sorry, along the jets, but also radially outwards in this way. So I'll show this picture 3 times just to bring out some of the structures. So if you make a force-free model of this, this is one in which the electromagnetic force density vanishes. There's no inertia there, nothing like that. It's just a pure pre-J.J. Thomson, post-Maxwell electrodynamics. You assume it's stationary and axis symmetric. There are these magnetic surfaces here, and they'll carry away energy and angular momentum. But instead, the conjecture is that there's instabilities that transport the energy across the field. If I go to this again, then you might say, well, what's happening outside this region here? Then there are field lines here, and I will call this a magnetic clutch. And you continue to transport the energy and angular momentum outwards, equatorially, not just up along the jet, but outwards like this, just like you do in an accretion disk. And if we look at a simple model of an accretion disk, this is just a simple model of an accretion disk. If it's a steady radiative accretion, the center of the disk transports energy and angular momentum outwards. There's a torque in the disk. It does work at a rate g omega, and energy is going outwards in the disk. And normally in a well-functioning accretion disk, you radiate it away, which is what astronomers look at. But if you can't radiate it away, there isn't enough gas to radiate it away, then you will unbind the gas. The energy released at the center automatically unbinds the gas. And so what I'm proposing is something that is a more extreme version of this, that essentially unbinds all the gas, not just enough to carry away a small amount of energy and angular momentum. So in this magnetic clutch, what you have is a spinning, essentially a spinning conductor in the middle of a large-scale magnetic field. It's a current source. It drives current, which constitutes the jet. and then it also transports energy and momentum outwards. And all of this gas, which was supplied at large radius, is blown away by the power of the spinning black hole. And if I put this in terms for M87, there's enough power in M87 to keep the Virgo cluster in the spin of the black hole in M87, to keep the Virgo cluster warm for 10,000 Hubble times. So there's plenty of energy available, and you only have to tap a little bit of it at this time. In the past, it was, when it was accreting very fast, M87 would have been probably the second brightest star on the sky. So you'd be your ancestors would have been navigating by it, perhaps. Okay, so it would have been a very bright source, but now it's very faint. Under these circumstances, the conjecture is that the jet blows away all of the gas. So instead of being an accretion disk, which astronomers have known and loved since the 1950s, I'm claiming that this is perhaps an ejection disk. Gas is supplied there and then blown away. That's what happens in this magnetic clutch. And it looks like there are instabilities that could be local and just transport energy and angular momentum, preserving more or less the structure, or you could, in the limit, develop a very large electromagnetic turbulence, which is much more efficient. So that's the radical view. And so here's the ejection disk, and a sort of more generalized version of this is those lines that I told you about are really gas that's being ejected from the disk. And so I'm clearly running out of, I must be running out of time. That,
No, you still have
5 minutes. I can, if I speak fast, I can get to the end of the talk. Okay. Okay. So anyway, so here we've got a flat spectrum radio quasar. This is 3C279. It's another type of quasar, and it's one of the ones that has been, I think, very important because Fermi Gamma Ray Space Telescope was able to show that this was varying on timescales of 3 minutes. Remember, we're talking about a black hole that's the size of the solar system, powering enormous radio lobes. But a black hole that's the size of the solar system, it takes more than 3 minutes for light to cross the solar system, and this varies in timescales of 3 minutes at gamma rays. And there's a real problem, because if there's a gamma ray that's made down here, very close to the black hole, the one thing we know about quasars is they're full of ultraviolet photons, because that's how we discover them. And there's ultraviolet photons there, and yet the gamma ray has to get up. And if you look on the back of a banknote carefully, it says, "In QED we trust." And you may not believe all the meteorology associated with the disks and so on, but we do believe QED. And gamma plus gamma makes electron-positron pair. There's a huge opacity there. So the way you have to do this in this context goes back to these boundary layers. There's a sufficient neutral material here in these sheaths here around the jet that it can protect the inner parts of the jet from the incoming photons. And so if we look down the jet, as we're prone to do, this is superluminal source, we look down the jet, then we can see the gamma rays getting out unimpeded by soft gamma ray photons. And actually, I'm also claiming in this context that gamma rays are synchrotron radiation, that's another heresy, but you don't want too many heresies. Okay, so at any rate, so this is the sort of standard view, if you like, also a sort of modified view that may or may turn out to be right, because all of this is decidable, I think, by observations. And as we have it at the moment, one of the things I'd like to emphasize is that this is inherently an international business. The Event Horizon Telescope, which is a glorious international collaboration, had to be such because you've got telescopes all around the world. Okay, and to make just to make that work is extraordinary. I mean, the technical skill that went into getting all these different observatories made for different purposes to talk to one another and make fringes and so on was fantastic. Here's Meerkat, which I've already said. Here's the Chinese telescope FAST, which is a work in progress, but already discovering great things. Here's gravitational radiation, which is part of the multi-messenger story. Here's radio astronomers exist. This is actually now no longer working, but we've been doing VLBI in space, so you get longer baselines, a better resolution, but at lower frequencies. And if we look to the future, The US entry is something called the Next Generation VLA. The international one is sometimes called the Square Kilometre Array. No one knows what these will look like asymptotically, but they're certainly large projects to push radio astronomy to the frontier. Low frequency, just shown schematically here, low frequency astronomy has a great future. And going into space with even more intent to do millimeter observations and with very long baselines, and thereby improve upon the spectacular image of the black hole in M87 I was just at some meeting where this was heavily discussed, and if you think you've got problems handling data, you want to think about trying to do interferometry from space and getting that data. The real challenges there for sure. And this is just a cartoon. Nobody knows what that will look like either, but it is clear that it is in our future. So my summary really is that radio astronomy began in Wheaton. Be grateful of it, and next time you drive through it, tip your hat to it. The extragalactic radio sources are jet powered. They're observed throughout all spectra. They're powered by black holes. I put a query here, but my view, and I think, and I took it to a rather extreme, was that it's the spin, not the accretion, that powers most of these jets. And you can anticipate great progress over the next year and the next decade as well with longer term projects. So it's a very exciting time to be thinking about the sort of reverse engineering of these sources and learning about them. So thank you very much indeed. I've enjoyed very much speaking. Thank you.
Yes, we have some time for questioning. So, Claude Mondre.
Thank you, Roger. So what is the relationship between this ejection disk model that you mentioned and the magnetically arrested disk model? Also involve magnetic.
Yes, the so-called, for those who don't know their acronyms, I've forgotten what's the other acronym that they use? I've forgotten. So I'm saying there's the sane disk and a mad disk. Well, this one is criminally insane disk. Okay, so it's not mad, which is sort of treatable, but this is one that's psychotic. And so it's a very extreme version. And for an observational astronomer, the claim, the assertion is, and this is what's distinguishable, is what the Event Horizon Telescope is observing is not a two-temperature, ion-supported thick torus, which I think will actually deflate now, but instead a magnetosphere, and the emitting elements are current sheets in that magnetosphere, just like they are in a pulsar. So it's a magnetically dominated region. Now, is there gas in it? Of course there's gas in it. Plasma is slippery and it'll get everywhere. But it's essentially the stresses there are mostly electromagnetic. That's the assertion.
Has this ever been simulated?
No.
Or is this a brand new idea?
No, but there have been 60,000 simulations in the Event Horizon Telescope of the alternative view, which I was one of the originators of this picture, so a long time ago. So I'm not as though I disavow it or anything. It's just I think that now observationally, for me, it is very hard to still believe in it because the source is so faint in some sense. And I'm more and more worried that plasma processes will take ion energy, give it to the much colder electrons, heat them up, and thereby deflate the disk. And so there are models, and they're serious models, and I showed you some of them, and they may yet turn out to be correct. But this at least is an alternative, and I think it's one that's well motivated by the observations.
Oh.
So, Roger, this is fantastic.
Oh, I didn't, Sasha! Yes, okay. I was looking out for you, and I completely missed you. So yes.
So how do you get an insane disk? Do you start with a sane that goes mad and then goes insane? Like, how do you envision it happen in the source?
Oh, yes.
No theory.
I think yes.
No. The way you do it. There's a larger story here, and the larger story is all AGN. But basically what happens, I would say, if I want to talk you through a story, is when M87 was the second brightest star in the sky, and you and your ancestors were navigating using it, then you would probably have an accretion disk that it's closer to Hammond. But then when the gas supply closes down, you've got this magnetic field there, and essentially you eject more and more of the mass. The less you accrete, the easier it is to eject the gas. And essentially we're in the limit where essentially all of the gas that's supplied, which is enormous at large rates, we see in M87, we see gas swirling around. We know there's a lot of gas supply there. And that essentially is all blown away by this flywheel in the center that's just throwing everything out.
So I'm really interested in how to get that transition from mad to insane, because we simulated MADs, which
I understand.
I think they do in exactly what you described. Mass accretion rate drops, but it still stays mad. So I'm really curious, like Claude is asking,
yes,
how do we go insane? I mean, not we, the simulations. So maybe we can take
we
that.
can talk about that afterwards, yes, but I'm sort of taking a less of a simulation-based view, but starting from a different place and asking about, let's imagine we've got magnetic surfaces. The ones that are most interesting are those that thread the ergosphere. A magnetic surface that threads the ergosphere has to be rotating. It has to be carrying away energy and angular momentum if it's sort of stationary and axisymmetric. And there's no obvious supply of energy. And my guess is that that's in fact unstable. In fact, you can sort of do electromagnetic Couette flow and so on and show sort of things that look like there's local instabilities. I can't do global instabilities without a simulation, but basically the way forward is to take that as a starting condition and then watch it go unstable. That's, just like one did with magneto-rotational instability. So that's the story I would tell. I haven't done that, as you know. I'm severely challenged in these simulation matters, but I have, I've got colleagues who are actually trying to set up that instability. Yeah.
Okay, Vicky. And then
No, go ahead, Vivian.
Oh.
So if you have a spin-powered jet, not an
Yes.
accretion-powered jet, would you expect the same fundamental plane relation between the radio and the X-ray behavior?
The radio and the X-ray behavior. I think the X-rays, you have to be a little bit careful because there's two sources of X-rays. One is the some that's attributed to a disk, and for example, in the Seaford galaxies, which are not radio sources, there you see these ion lines that are broadened, and it's really hard to imagine that those don't come from there are alternatives, but most people believe they come from a disk. So the ones that don't make jets make X-ray emission from the you see it from the disk. So you see that. But then there's also, as in M87, you see a lot of X-ray emission from the jets themselves. And so you have to distinguish those two, I think. So, it's generically true that more distant and more powerful sources tend to be powerful in the radio and the X-ray. And it's more, you often one's looking at a distance correlation rather than an intrinsic power correlation. Mm-hmm.
So just to make sure, your motivation for this alternative model is the fact that the source is not very bright, right?
But actually, it's more than that.
Okay. Yeah. So
I can lead you through very quickly when I first saw the image. This is the calculation I did. It's a pejorative calculation. It's one that, now I've got your attention, we can have a conversation calculation. But what I did was I said, well, the field ought to be a kilogauss. Now, in the models themselves, it's much less than that. But I just sort of said that's, if I want to make a really powerful jet, it's a kilogauss. Okay, so then I've got a kilogauss there. Then I ask what's the cooling time of a synchrotron emitting electron in a kilogauss. It's 30 seconds. I then say what's the power of the source, and I multiply that by the cooling time, divide by the volume, and that gives me the pressure of the emitting particles. The pressure of the emitting particles. Then I compare that with a magnetic pressure. That's 10 to the minus 11 if you follow that calculation.
And
Now we can say, well, what did they actually do in the simulations was that for various reasons they clawed back all that 10 to the minus 11 to make a model of the source. But that at least got me thinking about the alternative possibility that the whole thing really is magnetically dominated. What you're looking at is a magnetosphere, not a torus.
So you concluded that there should not be gas. Basically, there should be very little gas.
Very little gas, and it's all magnetically dominating. Then you say, well, what confines that magnetic field? It's like the first cosmology, which is, the flat Earth on the backs of turtles or elephants and turtles, and what do they stand on is more turtles, But it's the same with the magnetic field, more and more magnetic field. But ultimately, you've got to have some gas there to confine that magnetic field. It's not going to stay there by itself.
Yeah. Okay.
And so you really do need a disk there. But my contention is that it's on a scale larger than the EHT image.
That makes a little more sense to me, and somehow in my head this connects. Is this connected in some way to the fact that we see these jets for some sources extending over huge distances, where we know there is no accretion disk on those scales, and yet the jet is very highly collimated. And the gas there, there is some gas, obviously, but
yes, it's the same
like
thing.
An accretion disk.
Yeah.
So is this the same physics?
Yeah, no. The disk does not go out to more than 1 million gravitational radii, and the collimation is affected by magnetic stresses, magnetic tension, if you like, with field lines that are wrapped around, give you a tension like that.
Yeah.
Ultimately, that has to be confined. But the pressure you need to confine a luminous jet in the center by gas at much larger radius can fall off as 1/r squared. So if it's 30 times larger radius, the pressure that's actually confining this ultimately is 1,000 times less pressure than you're collimating in the center.
So just a quick comment. Do you expect to see these ejection disks moving out? Perhaps we could search for proper motion. Is there some ways that we can actually test this idea?
Oh, I think there are ways you can test it. I don't think they'll even the timescale of the most ambitious graduate student project, you're not going to measure any motion. I think
VLBI, for example,
I think it's not really so much. It's really seeing the outflows themselves. For example, the spatially resolved structures that are being seen by Genzel and ELT and so on, I think are very exciting in the shape of things to come. And with that gas, you have a kinematic choice. I like to call it in, out, round, and about. It's either something that's falling in, something that's going out, something that's orbiting, or something that's just chaotic. And I think we ought to be able to interpret these emission lines to see if they're outflows or not. I think that's probably a good place to start. And that I think is doable now.
Okay. All right, great. It's a little bit late, so I appreciate such a fantastic job you did for this talk. So let's thank Roger one more time.